you have a couple options here. If you have MATLAB access, well, then that's great. Just download or unzip the files that Dr. Rosen shared and place them somewhere where you can easily find them, or more importantly, where MATLAB can easily find them. Desktop is fine. If you don't already have MATLAB and you still would like to be able to follow some of this, you can download a free trial version of it. It is a large file, so if you're going to go that route, start right now. We're going to be spending at least an hour first going over some fundamentals before we get to the MATLAB portion, so you can finish the installation during that period of time. It'll probably ask you which toolboxes you want installed. At a minimum, you're going to need the parallel computing toolbox, statistics and machine learning toolbox, and optimization toolbox. Those three, I think, are going to be needed. Deep learning toolbox, it would be useful to try things that Emre is going to talk about tomorrow. If you do not have MATLAB and you'd like to be able to play around with it, the student version of MATLAB is an exceptionally good deal. It's $99 and includes MATLAB, Simulink, and 10 toolboxes, including the 3 that we're going to need today. And then each additional toolbox is only $10. Given that this software costs hundreds of thousands of dollars when universities purchase it, you can see what a great deal that is, if that's something that you're interested in. It's a perpetual license, so you have that for forever. At least for that version of MATLAB, you'll have it forever. So, okay, wow, we have reached 46 people. So let me let's get back. Let me reintroduce myself. Gail, is it okay? Can we get started? Okay.
Yes.
So, all right. So I am going to share my screen.
Real quick, just a welcome to all the new people. And yeah, so we're going to have the machine learning week this week with Dr. Polikar starting off. So take it away. Yeah.
All right. So give me a few moments. Let me, I have multiple screens that I am juggling here. So I let me set it to make sure that it will work. Let's share this. I just want to make sure that this is the one that I need to share. Okay, hopefully everybody can see this. And I'm going to rearrange certain things in my. Okay, so we're going to talk about fundamentals of machine learning today, more traditional topics of machine learning. And over the next 3 hours or so, and we'll have some interactive practical sessions as well. So this is the slide that I've shown at the beginning. Again, if you don't already have MATLAB and you'd like to be able to participate in that part of it, it's not absolutely critical, but I think you'll get a lot out of it. So that's the information there. So I want to, for those of you who might not be familiar with our institution, so we're located in Glasgow, New Jersey. It's about 25-minute drive from Center City, Philadelphia, and I'm with College of Engineering, Electrical and Computer Engineering department. So I want to start by saying that there are a number of different terms that are used to describe this field, and you might have seen one or more of these. A lot of people use these terms interchangeably. Pattern recognition, machine learning, artificial intelligence, computational intelligence. They're are some minute differences among these phrases, but by and large, they refer to similar terms. And we're gonna be formally defining what is it that we mean by that in just a moment. For the purposes of this discussion, we are really more interested in the pattern recognition part of machine learning. AI in general is a term that encompasses a little bit more. It includes things like data mining, formal theoretical methods. So we're not going to be talking about those. What we're really interested in is making decisions, classification decisions based on data, and that's essentially pattern recognition, recognizing patterns that the algorithm has seen before. So for those of you who are getting your feet wet with this, so let me start with this. So how many of these folks that you see in these pictures do you recognize, right? So you can just use your emoticons to raise hands or show a thumbs up or thumbs down. I suspect that most of you will recognize the first gentleman over in the upper left corner. If you're in Pennsylvania, you will probably recognize the second person. That's Governor Tom Wolf. If you're in New Jersey, you will recognize the third gentleman in there. That's Governor Phil Murphy. For those of you who've been in computers long enough, you'll recognize a somewhat younger version of the gentleman on the fourth picture. That's Bill Gates. But then things start getting a little more interesting. You may not recognize for everybody in the remaining pictures. So if I were to say, who's the gentleman on the first picture on the lower left? Who is that? And if you know the answer, just feel free to unmute yourself and just spurt it out. Who's that person?
Chris Christie.
Chris Christie. All right, somebody recognized him. Excellent. What about the gentlemen on the three gentlemen on the upper right corner? You recognize at least one of them, but do you recognize all three of them? Anybody who recognizes all three of them? I see Gail nodding her head, but anybody else? Okay. What about the swimmer on the second picture on at the lower part? Who is that?
Michael Phelps.
Okay, I heard Michael Phelps. Anybody else? Any other suggestions? You can put it on the chat windows as well. If you think you know the person, just spurt it out. I heard at least one person who said Michael Phelps. Anybody else? And if you also think it's Michael Phelps, go ahead and say, hey, yeah, I think it's Michael Phelps as well. Or if you think it's somebody else, say so. No other swim. Okay, I see a few people mentioning Michael Phelps. All right. We have Ryan Lochte. Okay, very good. So we have some swimming fans here. More Michael Phelps. All right. Okay. And I'll give you the answer in just a moment. What about the first young boy that's in the not the last one, but the second before the last one? Anybody who recognizes that? Oh, okay. And interesting fun. There's one person for Joe Biden. Any other guesses? And finally, the one at the far right, below right. And Kelsey says he's going to go out on a limb and guess it's you. Excellent guess. Yes, that is in fact me, a 5-year version of me, more specifically. All right. So the other one is indeed Joe Biden, by the way. Excellent guess, Venkata. But nobody guessed the swimmer right. That is not Michael Phelps, and it is not Ryan Lochte either.
Who is it?
Well, his name. Oh, hold on a second. Caleb Dressel is his name. And Caleb Dressel is the person who got a lot of medals in the last Olympics. But I picked and put him in there in particular, in fact, expecting Michael Phelps or Ryan Lochte to respond. So the point of this exercise is this. What a machine learning does is just about exactly what you have just done here. Right? So some of these people, you recognize them, even though you might not have seen this precise picture, because you have seen a version of these people, you were able to recognize them immediately. Others, you recognize certain features and you made a prediction. For example, you predicted the swimmer was Michael Phelps. Now, you made that prediction, again, based on your prior training, your brain's training, that is. You look at a swimmer and, you thought, well, okay, who's the swimmer, that a swimmer or any swimmer that I know, and many of you know the Michael Phelps name, and you predicted that. Now, that was an incorrect prediction, but not a bad prediction, given the information provided in there. Now, if you knew a lot more about Michael Phelps, you would have known that Michael Phelps does not have any tattoos. That was the big giveaway in that. Of course, only if you knew that particular feature of him. And we're going to talk about the term feature as well. Now, I can give you other examples. So these traffic signs, hopefully you will all recognize them. And most of them are self-explanatory, right? It says, no turn on red, or right turn signal, or do not enter, wrong way, speed limit 30, 40. But if I were to show you these, how many of these will you recognize? Well, some of them, again, even though these are not the traffic signs that we are using here in the United States, these particular signs are international European signs that are most commonly used in European countries. The text is in Turkish, so any sign that has a text in it, that is indicated in Turkish. But you would not necessarily recognize this because, well, you're not familiar with this. You have not been trained to recognize these. But you can make some inference on some of those. The blue ones that's show these arrows, you can probably make a good guess that it's go left, go right, and you can go left and turn and so on and so forth. Others perhaps you don't recognize. I mean, any guesses what? Let me see what's a good one that's not as easy to recognize. So, for example, I don't know if you can see my mouse here, but this one says 6. And then it shows an arrow on some axles. Any guesses what that might mean? I would not be surprised if you didn't know what that means. It means no more than 6 axles allowed on that road. So any vehicle that's longer than that is not allowed. So the point is, your predictions are as good as the training that you have received in the past in recognizing these images. And the same thing applies to machine learning as well. Any machine learning system is only as good as it is trained, or the data that it has seen during training. So we're going to make a big deal out of this during this this lecture. All right, so let's try to define it, right? So what is machine learning? Now, there is no shortage of definitions. I mean, you can find lots of definitions in various different places. An informal definition that I kind of made up is the following. It's automated analysis of typically large volumes of data in search of hidden structures, patterns, or information based on training with prior representative data. So you have a representative data that's available to you. You use that to train a machine learning system, and then you ask that system to make predictions or inferences on other data that presumably is similar to the one that it has seen for training. Pattern recognition is a specific type of machine learning where you are classifying objects into predefined categories or classes. There are multiple formal definitions of this. I put the one from Wikipedia as well. And these definitions reflect the time when the definition is made. So if you look at the 1959 definition, that's the oldest definition that I could find. It says the field of study that gives computers the ability to learn from data without being explicitly programmed for that task. If you look at the 1997 definition, and that's a computer science professor, Tom Mitchell, a very, very computer science-y definition, not a very engineering definition, but a computer program is set to learn from experience E with respect to some class of tasks T, and the performance measure P. If it is performance at task T as measured by P improves with experience E. All right, so if that makes your head spin, fine. Just use my informal definition at top. Okay. Now, the applications of machine learning is well. I mean, that's a very brief, abbreviated list that I'm putting up there. It is growing by the day. You are probably hearing more and more and more every day about various different types of applications of machine learning, and perhaps that's why you're here in this workshop in the first place. So those are the applications that I have put on this slide. Are just random ones that came to my mind, and these are more traditional applications, but there are many others. There are many others, and we'll talk a little bit about those as well. Machine learning can generally be divided into three major subfields, if I may call them. The two most common ones are the supervised and unsupervised learning. Supervised learning simply refers to the fact that you have previously labeled training data available to you. That means there is a data set, and for each data, there is a label or a classification that's being provided to you. And as far as you're concerned, that label, that classification is correct. Okay. So anytime you use such a data to train a neural network or to train any machine learning, that's called supervised learning. And classification is essentially an application of supervised learning. Unsupervised learning is where you have data, but it is not labeled. So you just have data. Then the typical thing that you would do with such data is clustering. Since you cannot do classification, since you don't have any class information, you don't have any label information, all you're doing is putting like data into a same cluster. And then there's a third category of machine learning, and that's reinforcement learning. That's a very different animal. And in reinforcement learning, it's not supervised or unsupervised. There is usually learning from experience. The data comes in real time, and all the learning algorithm have access to at that time is success or failure. So very commonly used in gaming applications. Imagine that you are playing chess, or you're trying to learn how to play chess. You know the rules, but you don't know the goal of the game, and you don't know certainly have any strategies. So you're playing against a person who knows this very well, and that person says, "Let's play." Again, all you know is how the pieces move. So you make a move, your opponent makes a move, and you keep going on. At some point in time, randomly, your opponent tells you, game is over, you've lost. And now you do it again, and again, and again, and again. In each case, in each time, there is a different set of moves being played. And of course, you keep losing it, perhaps because you don't even know what the goal is. And then you repeat this thousands, if not millions of times, and for some random play, the opponent says, you won. And that is the only information that you have. So by playing this over and over and over and over, you eventually figure it out what the rules are, what the goal is, what the strategies are. And that's called reinforcement learning. Very commonly used, again, as I said, in gaming application, also commonly used in a lot of real-time decision-making applications. Autonomous driving is another excellent application of reinforcement learning. Now, for the purposes of bioinformatics or biological data sciences, the part that is most common to those fields are supervised and unsupervised learning. I just mentioned reinforcement learning simply because it is a growing area of machine learning as well. But from a bioinformatics perspective, there are some major areas of applications for using machine learning in data sciences. Phylogenetics or molecular evolution is one. Protein structure analysis is a huge area of biological data sciences where machine learning is used. If you follow that area, just recently, a company called DeepFold came up with an algorithm that can predict the folding structure of any protein. That's a huge deal for a lot of folks who work in that area. Disease research, being able to diagnose a specific disease, perhaps from its genetic factors, is another application where machine learning is commonly used. Common machine learning algorithms and how they're used in biological data sciences is shown in this particular slide. You'll see that it's split into two. There's supervised learning and unsupervised learning. You see some acronyms in there. It says SVM, KNN, PCA, CNN. We're going to talk a little bit about some of those things, and some of them we'll talk about them tomorrow. So SVM is support vector machine. We'll chat a little bit about that today. KNN is k-nearest neighbor. We're going to talk about that today. CNN is convolutional neural networks. We're going to talk about those tomorrow. K-means is a clustering algorithm. We're going to talk about that today as well. And there's many others. Obviously, we don't have time to talk all about those. So that's roughly what we're going to be doing today and tomorrow. We'll introduce you to some of these algorithms. Not to the mathematical gory details of it. I don't think that would be of terrible use at this time, but the general idea, what that algorithm does, and then we'll show you how you can use them in practice. Now, when we polled the audience the other day, about a third of you mentioned that you had no previous machine learning experience. About a third of you said you have very little, and about a third of you said some. So I'm going to assume that most of you have no experience. I'm going to start with some terminology so that we are all on the same page, so that everybody understands what we say as we move forward. And these are the common vocabulary that we use. Feel free to stop at any time if anything is not clear to you. You can put something in the chat, or just unmute yourself and ask to clarify. Okay. So classification is identification of any object into its correct category based on its features, and we're going to talk about features in a moment. So here's a very simple example of a classification, right? Imagine that we are trying to determine whether an applicant is worthy of a loan or credit, and I have two pieces of information. I'm going to call these features in just a moment, and I know whether I know what their income is, and I know how much savings they have. Okay, so if I were to plot these on a two-dimensional graph, income versus savings, and every red and purple circle there is a person, and let's suppose that this is the data that I have. And if I am the loan officer, I can say, well, you know what, I'm going to consider anybody who has income less than theta 1 or savings less than theta 2 as high risk. And anyone who has an income greater than theta 1 and savings greater than theta 2, I'm going to consider them as low risk. There you have a classification rule, right? So if income is greater than theta 1 and savings is greater than theta 2, then it's low risk, otherwise it's high risk. That is a simple classifier that you can use. For a classifier to be a classifier, you have to have class labels, definitions. In the previous case, it is low risk, high risk. If you don't have such labels, then at best what you can do is clustering, and that's given data of objects obtained from an unknown number or categories. You group them in such a way that similar ones are grouped in the same cluster. Okay. So if I were to show you those blue circles, you may perhaps cluster them into those 4 clusters, thinking that, well, they look alike or they are similar in one way or another. Now, we did mention supervised and unsupervised learning. So supervised learning is where you have training data with labels. Unsupervised learning is you have data and no labels. There is something that's in between semi-supervised learning that's similar to supervised learning, but this time you have very little labeled data and lots of unlabeled data. And that's something that shows up in biological data science applications as well. And then, of course, reinforcement learning is an entirely different process. Now, I mentioned feature. So let's formally define what is it that we mean by that, because that's going to be important. A feature is any variable or an attribute or a predictor, anything that you believe that carries discriminating or characterizing information about the data. Okay. A feature vector is a collection of such features, and the feature space is a space in which such feature vectors lie. So, for example, a feature could very well be the number of ACGAs per million of base pairs. Another feature may be another former, a 4-letter k-mer, the number of CCGTs that are appearing in any given genome per million base pairs, and so on and so forth. So each of these can be a feature that I use perhaps to identify an organism. I put 4 of those together, and that becomes a feature vector. A 4-dimensional space where this feature vector lies is our, well, feature space. A class is the category to which any given object or data point belongs. In later slides, I'm going to be referring or denoting a class using the letter omega. A decision boundary is a boundary in that d-dimensional space that separates different classes from each other. So if I have 2 features, I'm in 2-dimensional space, and that's what you see here. There are 4 classes indicated, green, red, blue, and black, and the dotted line that separates them is the decision boundary. The job of a machine learning algorithm is to find that decision boundary. To do that, we use training data, and that's data that's provided to you ahead of time, where in the case of supervised training, the labels are previously known. So some expert or some oracle have looked at this data and labeled it for you, and that's training data. We will also talk about test or validation data. And this is the data that you have available with the labels, but you don't use it for training. You set it aside to test the performance of your classifier to see how well the training was done. And then, of course, field data is the unknown data to be classified for which the classifier is ultimately trained, right? The correct class for these are, of course, not known, and it is the job of the machine learning algorithm to tell you what those are. If a data point is incorrectly labeled by the classifier, that's an error. If there's a cost for making an error, that's the cost of making that error. Now, as we'll talk a little bit later, is not all errors are equally costly. So you may want to consider that in the design of your machine learning algorithm. For example, if you are trying to develop an algorithm that will diagnose based on, say, some image, whether there's a malignant tumor or not. Well, the two kinds of errors that you can make there is the tumor is malignant, but your classifier says, no, it's not. Or the tumor is not malignant, but the classifier says, yes, it is. As you can imagine, those two types of errors are not equally costly. So we'll talk a little bit about that. A confusion matrix is a matrix we use often in evaluating classifiers. It is a K by K matrix where K is the number of classes, number of categories that you have. The rows represent the correct classes. The columns represent predicted classes. So C11 is the number of instances in your data set that belongs to class 1 and correctly identified as class 1. C12 is those number of data points in your data set that actually belongs to class 1, but your classifier said class 2. So the number of instances in this and the diagonal part of this matrix are, of course, your the number of correctly classified instances, whereas everything else is incorrectly classified. So you want a confusion matrix that is purely diagonal, if at all possible. All right, with that classification out of the way, let me throw some common machine learning algorithm names at you, and we're going to talk about some of these things. On the classification side, again, that's where you have labeled data. You have Bayes classifier, and a subset of this is the naive Bayes classifier. And we're going to spend a little bit of time on that because, well, you'll see why in a moment. K nearest neighbor, discriminant classifiers. Neural networks is a huge field. I should say a group of algorithms under machine learning algorithms. There are many types of neural networks, and we're going to talk a little bit about them. There are kernel methods. Support vector machine is a good example of that. And then there are decision trees, and we're going to talk a little bit about those as well. On the clustering side, there's K-means, there's fuzzy C-means, there's adaptive resonance theory. This is by no means an exhaustive list. There are lots of them, but these are perhaps some of the more common ones. If we were to live in an ideal world, the data that you have would be something like the one that appears here on the left. That is, the features are such that they are easily separated. That's easy to distinguish. But in reality, most data looks more like the one on the right, where the instances overlap. So creating those or finding those decision boundaries are not that easy. So it will be the job of the machine learning algorithm to find those decision boundaries that makes the fewest error. For that, we need to pick good features, right? Good features are those features that distinguish between classes, and bad features, of course, are those that don't. And if features are such that they allow linearly separable, as the lower left here, those are the easiest ones for classifiers to identify. Non-linearly separable data are still okay. So is even multimodals. So that means it requires a multiple decision boundaries just to separate two classes. So we're going to start with a hypothetical toy example just to ground ourselves. And I picked an example that I hope that will relate to many of you who are in biological data sciences, and that is taxonomic classification. And here we are given a long sequence, their genome, and the question is, given a genome, which genus does it belong? Who is this genome belong to? To make things simple, let's pick two features. Let's assume, simply for the sake of argument, that we're going to use two features. One of them is the number of genes per read and the average gene length per read. So you have a sequences that spits out reads, say of length 400, whatever, or maybe less, maybe more. And those are the two features that you think are relevant. And the first thing you want to know is which feature is the better one. So you create a histogram, okay, for each of those features. Let's call them X1 and X2. And you see that on the left, if the value of X1 is, say, 10, there are this many, say 8 from genus 2, red. There are 12 of that from genus 1. If the X1 value is 20, there are 22 of those from genus 2 and say 10 of them from genus 1. So if that is all the information you had, your decision boundary would be, well, I'm going to pick this here, say 11. If it is less than 11, I'm going to call it genus 1. If it's greater than, I'm going to call it genus 2. Now you do the same thing for your second feature, and you find this kind of histogram. Based on this, which feature is better? Again, just unmute yourself, spur it out, or put it in the chat window. What's the better feature here? And why? All right, a couple of you said feature 2. And why is that the case? Less noise, okay. Better distinguishes the two genuses. Yes, right. I mean, you can see that there are fewer mistakes, better segregation if you use the second feature. All right. Now, of course, if you only had two features and you have the ability to look at them like this, then it's easier. All right. Well, let's do this. You decided that maybe instead of using just one feature, I'm going to use both features. And now you use both features and you plot a scatter plot of those two features, and you see that the data looks like this. Now, all three of these have the exact same data here. Okay, it's the same data. And you have three different possible ways of distinguishing this data. On the upper left, one is just a linear boundary. On the right, with number 2, is a very intricate boundary that makes no errors, right? And the third decision boundary is a curve, does make some errors. Anything to the left and it is red is incorrect. Anything to the right of the boundary and it is black is also an incorrect decision. So if you had these three different decision boundaries or three different classifiers, really, which one would you pick? The first and the third one make some mistakes. The first one makes the most number of mistakes. The third one makes fewer mistakes. The second one makes no mistakes on this training data. So if you had these three classifiers, which one would you pick as your, all right, so let's see. Well, somebody says it depends. Okay, depends on what? Somebody says 2, somebody says 3, 1 or 3, depending on the training and testers. Based on the situation, I would choose 3. All right, so I've heard some answers from both 1, 2, and 3. So for those of you who have done any machine learning, you probably know number 2 is the worst choice here. And that is because of, all right, somebody just called it, was overfitting the data. In other words, the model in number 2 has learned the noise in the data, not just the information carrying part of the data. So what's happening in number 2 is, as I said, overfitting. So perhaps another example of that is here. Imagine that you have these data that are indicated with blue circles, and you want to know what function they represent. Okay, and you think that a polynomial function in this form, you know, omega 0 plus omega 1x, omega 0 x, omega 2x, 2x squared, and so on and so forth, can be a good general function. The question is, how many terms of this function should you use? If you use, if m is equal to 0, then your model is just y is equal to omega 0, which is this, the first one, which is a flat line. If you choose m is equal to 1, then your model is omega 0 plus omega 1x, which is a linear model. If you choose m is equal to 3, then you have a third order polynomial. You have 4 parameters, omega 0, omega 1, omega 2, omega 3, to adjust. If you choose M9, then you have this kind of a model. Now, you will all agree with me that m is equal to 9 is probably not what that data represents. Now, what that data does really represent is the green curve. Now, of course, that's unknown to you. But you can make a prediction thinking that, all right, the one that's represented with m is equal to 9 is clearly overfitting. In this case, probably the best answer is 3, because that's best captures the characteristics of the data without overfitting. Now, overfitting is important, and it goes all the way back to Occam's razor, a philosopher from 13th century. Said entities are not to be multiplied without necessity. The original in Latin is indicated at the bottom. I'm not going to even attempt to pronounce it. But it is one of the most important concepts to understand in machine learning, because a lot of algorithms overfit. Now, and we're going to talk about how you can protect against overfitting. Now, a classifier is, of course, intuitively designed to minimize error. But if you minimize error too much, then you run into this overfitting problems. We did talk about errors, and that the fact that not all errors are equally bad or equally costly. Depending on how critical those different R's, you may want to even adjust your decision boundary. So if you go back to our example here, if you were to pick this one as the best boundary, but perhaps you really don't want to make the error of misclassifying one of them, say the red ones, you can move your decision boundary such that you will never misclassify a red one as a black one as a red one. But by doing so, you increase your chances of making the opposite of error, which is misclassifying the red ones as black ones. Okay, so we're going to be considering in weighing our cost function to make sure that the overall cost of the algorithm is minimized. All right. A few more things before we get into the classifier. So this is your typical process in designing a machine learning algorithm. You will start with data acquisition. That's your data. You'll clean that data if there's noise in a process called pre-processing. Now you extract features, and those are the things that that part of the data that you feel is most informative. And then the classification, that's training of the classifier or identifying the model. And the post-processing is adjusting your model, determining whether your model is good enough or not. And based on that, you can go back and you can make some adjustment. So this is your general pipeline in designing any machine learning algorithm. All right. So this is my last slide in this first part of this lecture before we get into the algorithms themselves. I mentioned there are lots of algorithms out there. There are probably literally hundreds, if not thousands, of different machine learning algorithms, each varying from others in some meaningful way. You may want to know which type of classifier is the best one for your application. To put it in this proverbial question, you know, if you were stranded in a desert island and you could only bring one classification algorithm, what would that be? Now, for those of you who have any experience with machine learning, tell me what is your answer to this question. If you had only, is there a classifier that's your go-to classifier, you know, that you would use before anything else? Or if you could only use one, that would be it. Or is there a classifier that you think is better than everything else? If you have such a favorite classifier, put it on the chat room. All right. I see somebody put random forest. Somebody said there is no one best classifier. We'll answer that question. I have another random forest. Anybody else? So if you've used machine learning algorithms, spit it out. Just type it in. If you haven't done anything, then you know we'll give you the answer. All right. Let's see. If I have enough data in neural network, says Dr. Rosen, it depends on the data and the research question. Certainly, but if you're in a deserted island, you don't really have that choice. Let's see. While it really depends on the data, I can see the appeal of random forest if you only have one. Some have limitations, and you never know what future data you have. Yeah. So I see some people like random forest, and look, I like them too. I think random forest is a good one. But if you were to ask, is there a best classifier out there? Well, there is an answer to that question. One of you said there is no best classifier. There's truth to that answer, but there is also something else I'm going to share. Somebody said, is LR and ML by LR? I don't know what you meant by it. Did you mean reinforcement learning? That's RL, or I'm not quite sure. If you could describe what you meant by LR, I can answer that question. Linear regression. Yes, of course. Machine learning is a generic term that you can use to represent any model that is determined based on data, and linear regression is most certainly fits in that definition. All right, I'm going to talk to you a little bit about Bayes decision theory. Statistically speaking, there is a best classifier, and that's Bayes classifier. So now it's based on the Bayes rule, and the Bayes rule is hopefully most of you, if not all of you, have seen this Bayes rule at some point in time in a probability class. It answers the following question: given an event A has occurred, what is the probability that an event B has also occurred where A and B overlap? Right? And here, in the context of classification, event A is an observation. You observed some data. Event B is that data belongs to a particular class. Right? the joint conditional probability is what is given by the Bayes rule, and it is expressed in that equation in there. If you have two events, A and B, probability of B, given that probability of A has happened, is given with that expression. We're not going to go into the equations. I'll just give you an overview of this, but then I'll also make these slides available as well. Now, this the Bayes classifier is based on Bayesian way of thinking, and it actually has an interesting history among those in folks in statistics. There's even a classical war in statistics in the definition of probability. So there are frequentists and there are Bayesians, and these two people don't necessarily get along very well. To a frequentist, the definition of probability is the expected likelihood of an event over a long run. So if something has happened lowercase n times out of capital N trials, the probability of that event happening is n over n. Okay. A Bayesian way of thinking is different. They look at this as a measure of plausibility of an event happening given an observation that provides you incomplete data and some previous belief that you have about that event. Now, I'll explain what I mean by that in a moment, because that's going to be important. Now, many phenomena, natural phenomena, can be explained by the frequentist definition of probability. If I were to say, what's the probability of hitting the jackpot in a lottery? Well, you know the total number of possible plays. 1 divided by that total number of possible outcomes is the probability. If I were to say, what's the probability that there'll be at least 10 non-rainy days in Philadelphia in October, I can compute that using a frequentist approach. I simply look at 100 years back. I count the number of years where there were 10 non-rainy days in Philadelphia in October. That divided by 100, well, that's the probability. Okay. The probability that the sum of two cars will be 21. All of these can be computed by this frequentist definition of probability, but some cannot. So the probability that a major catastrophe will end life on Earth in the next 100 years. It's not like that there are multiple examples of this happen that I can count, right? Or the probability that the conflict in Syria will end by 2025. Or there will be another major recession in the next 10 years, or there will be another pandemic in the next 20 years. These are not easy to compute using frequentist approach. And that's where the Bayesian way of thinking comes in, because you can make some approximate estimations of such probabilities. So in Bayesian thinking, we compute probability based on 3 pieces of information. And those are prior, likelihood, and evidence. Prior is your subjective degree of belief that that event is plausible in the first place. How plausible is this thing? Based on your own experience, right? It doesn't have to be mathematically grounded. Likelihood is the probability of making that observation, any observation, under the condition that the event has occurred. In other words, how likely is it to observe what I have just observed? How likely is it that I observe this data if, in fact, event A has occurred? Or, in the context of machine learning, how likely is it that I observe this feature value 5 if, in fact, it comes from the class X? So likelihood describes what kind of data you would expect to see in each class. And evidence is the probability of making such observation. In other words, what's the probability that I will observe X is equal to 5? So by using these 3 pieces of information, using this expression here, you compute the posterior. Likelihood times prior divided by evidence. Okay. Now, let's look at the fossil-based energy example that I mentioned here. The probability that the fossil-based energy will be obsolete in 50 years. What's the probability of that? Well, if I asked this question in early 1900s, such a phenomenon would not be on anybody's radar. So the prior that the fossil-based field will be obsolete would be 0. I mean, that would be unthinkable, right? In 2022, that prior probability is now much higher because we have other alternative energy sources. We still rely on fossil-based fuel, but the likelihood of no more fossil fuels, given that we have solar energy, now that's a higher. So using that prior, we can compute the posterior, which is what is the probability that there will be no more fossil given the current solar technologies. That will be very high. Statistically, this is the best classifier you can build. So is there an answer to the question, is there a best classifier? Yes, there is an answer to that question. That answer is the best classifier. Okay. Again, statistically speaking, and you can prove this theoretically, that is the best classifier you can build. This classifier is based on quantifying trade-offs between various classification decisions using a probabilistic approach. Now, but it makes two assumptions. One, that decision problem can be posed in probabilistic terms. And this is not a bad assumption. Just about any problem can be posed in probabilistic terms. And then the second assumption is all relevant probability values, those three things, right, are known or can be estimated. And that one is, in practice, not true. So if you go back to our previous example, we want to predict genus 1 or genus 2. Let me indicate them as class 1, class 2, omega 1, omega 2. Assume that you know the prior probabilities of each genus for a particular area, say in North Asia. You know that how often genus 1 occurs, how often genus 2 occurs. You can give them probabilistic values. Well, that's your prior probabilities. If that's all the information that you have, here's a decision rule. You pick class 1 if the prior probability of class 1 is greater than class 2. You pick class 2 otherwise. Now, if you have no observation, that is a meaningful. I'm going to just meaningful classification rule, perhaps. But now you make an observation, all right? Let's say that you observe a random variable, say the number of a particular Kmer occurrences, say ACC, GCC, T. And now you say, all right, I've seen 14 of this in my data. Now, how would that change your decision? Because now you've made an observation. So that will change your decision using this expression here. You can only look at the left side of it. Probability of omega j given x means, given that I observe the data x, what is the probability that the correct class is the jth class, if you have many classes? And that really comes down to these three pieces of information. Probability of omega j, so that's the prior probability of omega. Remember, that's your belief. That's your gut feeling, if you will. This is the likelihood, the probability of observing that x if omega j were true. And the last one is observing that value of x in the first place. And I will tell you that actually third one does not even come into play because that's independent of the class. So you really need to know these two values. This one, the probability of omega j, again, that's based on your prior information, prior experience, gut feeling. So that's easy to obtain. This one is the only one that we need to compute, the likelihood. So how do we compute that? Well, it's actually not that difficult for our example. Again, let's assume that we have two classes, genus 1, genus 2. I'm going to represent them in black and red, right? And probability of x given omega 1 will be the likelihood or class conditional probability for genus 1. And probability of x given omega 2 will be the second. Okay. Let's say that I made an observation. I pick a read and I see that the Kmer 1 occurs 12 times. I put a dot in there. Then I make another observation. Let's say it occurs 5 times. I made another observation. Oh, another 11 times, and another one, and another one, and another one. I create a histogram for both classes from my training data. And this histogram then gives you those class conditional probabilities, the likelihoods. Okay. So creating this likelihood is actually relatively easy. Simply create a histogram of the data. And then you multiply that with the priors. And then the final decision is simply the class that has the higher posterior probability. So for example, if I pick another read and there are 24 occurrences of that k-mer in that read, in that sequence, I go look at my posterior probability graph here, and I see that the posterior probability for the red is 0.1, for the black class 1 is like almost 0.9. Since this posterior probability is higher than that posterior probability, I pick class 1. And and that's my decision. And this is the Bayes decision rule. Choose class I if the posterior probability of class I is greater than the posterior probability of all other classes. That's the Bayes classifier. And computing this is not that difficult, as I just shown you. Okay, choose the class that has the largest posterior probability. That, my friends, is the best classifier you can build. So if that is the case, you may ask, well, then are we done? Can we go home? Is this lecture over? That's the best classifier. Well, not quite. The Bayes classifier cannot be used if you don't know or compute those probability distributions. Okay, probability distributions can be computed if you have enough data or lots of data, but it becomes increasingly more difficult as the dimensionality of the data increases. And this is known as the curse of dimensionality. Now, to explain what I mean by that is this. So if you have many dimensions, instead of just one feature, you have, say, D features, your probability of X becomes probability of bold X, where bold X represents not just one feature, but now you have D separate features. The Bayes rule looks like this. I just replaced X with bold X, and bold X simply says that X is not just one value, but it is a collection of D values, or you have D features. The change in equation is very simple. It's just a notation change from a non-bolded X to a bolded X. But the implications of this is very, very significant. Let me demonstrate what I mean by that. Now, in order to compute these distributions, these probabilities, I need to create a histogram. In order to create a histogram, you need training data. And the more data that you have, the better the histogram. So you need enough number of data to populate that histogram. So imagine that in one dimension, I divide my data into these bins. And let's say, just for the sake of argument, I need 30 examples for each of the 20 bins here to populate this histogram. So I need 600 observations to get a good guess, good representation of this one-dimensional histogram. Now, if I have two such features, not one, but two such features, then I still need 30 instances for each of the 20 bins. Now I need 12,000 observations. So now just to go from one feature to two features, I need 12,000 data points to reasonably estimate that histogram, that probability. If I have 3 features and to reasonably populate this histogram, I need 240,000 observations. Now, you can see how quickly the amount of data that we need just blow up. And that is why the Bayes classifier cannot be used in most cases. Okay, it requires a lot of data, and oftentimes you're dealing with hundreds, if not thousands, of dimensional data. So it becomes impractical. Well, that sucks. So we wasted a perfectly good hour on something that we cannot use. Well, not quite. We'll come back to the Bayes classifier in our second half, and I see somebody asking for a quick break. So we're going to stop here for just a few minutes, and I'm going to leave you with this top 10 classical machine learning algorithms list, and we're going to be looking, not all of them, but we're going to look at about half of these in the second part of this. So let's take a 5-minute bio break, if you will. Let's see. My time is 7 after 2. So let's come back at 12 after. Okay. So take a 5-minute break, and then we'll start with these different machine learning algorithms. Okay. If there are any questions in the meantime, I'll be here. Go ahead and ask them on what we talk about. You can put them on the chat box. So one question: if we have a lot of data, is Bayes classifier better than neural network? Everything being equal, Bayes classifier is always better than anything and everything else, if in fact you can implement this. When you say a lot of data, now we need to really explain how much data we're talking about. I gave the example, a hypothetical example of 3 features requiring 250,000 of data points. That's just 3 features. With 4, it's just going to become millions. If you got 5, it's going to be like probably tens of millions. If you have 10 features, it's going to be billions. Okay, a typical machine learning application has, at a minimum, dozens and dozens and dozens of features. Some of them has hundreds of features. Some of them have thousands of features. So with that number of features, a Bayes classifier is simply impractical. That you simply cannot calculate the necessary probabilities. So then, while statistically, Bayes classifier is better if you could implement it, but you can't implement it. So something that you cannot implement is no use to you. So the practicality of the matter is, of course, a neural network is better than that, only because you can implement it. Does that make sense? So how does Bayes classifier deal with outliers in the data? Is it just factored in the error? And, absolutely. Absolutely. So a Bayes classifier does not mean a classifier that makes no mistake. Make no mistake about it, Bayes classifier does make mistakes. Okay. And if there are outliers, those will most likely be misclassified by the Bayes classifier. But statistically speaking, Bayes classifier will make less error, or will have a smaller error than any other classifier, if it is, again, properly designed. Good question. Very good question. Now, you'll see that the number 9 on that list is naive Bayes, and we're going to talk a little bit about that. And that is the reason why we spend a little bit of amount of time on the Bayes algorithm, because we're going to make a little tweak that will make Bayes classifier implementable. But that tweak comes with certain strings attached. And And naive Bayes is a very, very popular classifier. Any other questions before we get started? Now, this list is not my list. The list originally appeared in that paper that I cited. You'll notice that that's a fairly old paper. That's 2008. And the number 6 there in the original list was not multilayer perceptron, but rather another decision tree algorithm that itself was developed by one of the authors. So I felt that it is just being a little bit narcissist in there. So I replaced with multilayer perceptron / deep learning structures. Of course, deep learning algorithms are more modern neural network architectures, but they are based on the multilayer perceptron. The algorithm is, its foundations lie on multilayer perceptron, which we're going to talk about here. Where's Learn++ and S? Gail? Well, as the person who developed Learn++, I wouldn't put in the top 10 algorithm. However, Learn++ shares a lot of bones, if you will, with AdaBoost. And AdaBoost appears as number 1 on that list. And AdaBoost is actually a generalization of random forest. So for those of you who have mentioned random forest earlier, one could argue that random forest is a special case of AdaBoost. All right, so let's look at some of these algorithms. I'm going to start with k-nearest neighbor. This is perhaps the easiest classifier you can build. And very, very simple approach. And I will explain how this algorithm works in the next 60 seconds. Imagine that you have this data that you see here. There's 4 classes. Okay, it doesn't matter whether it overlaps or not. So just for the sake of argument, imagine that this is the data. Okay, so this is your training data. That is, you know the correct labels. Okay, and now imagine that I have a new data point that I want to classify. Let's say that that data point is this purple diagonal, purple parallelogram. Okay, I pick a k. K is an integer, usually not an integer multiple of the number of classes. So in this case, there are 2 classes. I don't want k to be an even. I pick a k, an odd number, for the reason it will become obvious to you very quickly. I pick a k. In this case, k is equal to 11. I'm going to find the 11 nearest neighbors of this data point with respect to some metric. Okay, and that metric could very well be how close it is. So here, I don't know if you can see my cursor here. Can you see my cursor? If I move my cursor, can somebody put it in the chat box saying yes or no? Yes, excellent. So if this is the test data that I don't know what class, all I need to do is find the 11 data points that are closest to this, and those 11 data points are represented using this circle. And I simply count how many of each class are there. 1, 2, 3, 4, 5, 6. There are 7 green ones, 4 black ones. So there are 7 nearest neighbors of this data point that are green to 4 that are black, and I'm going to classify this as green because there are more nearest neighbors of that class for that. Here's another example. If this plus sign was my unknown data point, I count the 11 nearest neighbors for this, right? And now those are represented in this circle here. There are 2 red triangles, 3 black stars, and 1, 2, 3, 4, 5, 6 blue circles. And therefore, this data point would be classified as blue class 3. That's it, folks. That's KNN, K nearest neighbor. It's known as lazy classifier because there is no training. Unlike a neural network, there is no training. We didn't do any training. we went straight into testing. Given the training data or labeled data, you can immediately make the classification LUCMA, no training needed. Okay. This is a supervised algorithm because it requires labeled training data. Its pros, this is an algorithm that is unbelievably accurate. It is robust to outliers and no assumptions made. So considering how simple it is an unbelievably good classifier. Of course, there is no free lunch, right? It is a computationally very expensive algorithm. As simple as it sounds, excuse me, it is not an easy it is easy to compute, but it requires a lot of computation. Why? Because how do you find its k-nearest neighbor? In order to find its nearest k-nearest neighbor, you have to compute how distant this data point is from each and every one of these data points. You have to calculate the distance for all of your data and then sort them, and then the top 11 are your k-nearest neighbors. So it's a computationally an expensive algorithm. Okay. In MATLAB, it is the fit-cknn function implements this algorithm. Does this make sense? Right? Simple enough? Given training data, all you need to do is calculate its nearest neighbors. That's it. That's all there is to it. But it is suspiciously effective in doing what it does. Okay. All right. So that's KNN. So let's look at naive Bayes. Now, remember, we spent a good 20 minutes or so on the Bayes classifier. And at the end, we said, yeah, it may be the best classifier, but hey, you can't use it. So what naive Bayes does makes a naive assumption. And that naive assumption is that the individual features are class conditionally independent. Now, if that is the case, then the joint probability distribution can be written as product of individual probability distributions. The joint probability distribution that has a bolded X is very, very difficult to compute because it requires lots of data. But a one-dimensional likelihood probability distribution that only has, remember, this is unbolded X, that's easy to do. We did this just a few minutes ago when we generated that histogram. Okay, creating one-dimensional distributions is easy. Creating d-dimensional distributions is not. But if the d-dimensional distribution can be computed as product of one-dimensional distributions, and since each one-dimensional distribution is easy to do and doesn't require as much data, I can compute my d-dimensional distribution as product of one-dimensional distributions. But that is only true if this equation is correct, if and only if the features are class conditionally independent. Now, are the features independent? If that's the case, then naive Bayes is identical to Bayes, and it allows you to implement Bayes classifier without requiring as much data. Now you can ask the question, let's give another simple example. Let's assume that you're trying to decide whether a person is at risk of heart disease. And the two features that you're looking at are, let's say, blood pressure and cholesterol levels. Are blood pressure and cholesterol levels independent of each other? The answer is no. People who have high blood pressure also tend to have high cholesterol levels. Not necessarily, but there's a correlation. They are not independent of each other. Or perhaps age and blood pressure. Those are not independent either, because people who have as people age, their blood pressure tends to increase as well. So if those were the features the assumption that we've made for the naive Bayes would have been violated. But guess what? This algorithm appears empirically, experimentally, quite effective and quite what is the word I'm looking for? Robust to minor violations of that assumption. In other words, the algorithm works surprisingly well, even in such cases when we know that the variables or the features are not independent. Technically, it requires independence, but if there are minor violations of that, then it works surprisingly well. Okay. Now, I provide a pseudo algorithm, pseudocode for those of you who may want to implement this using whatever programming algorithm that you want to use. So this is the naive Bayes classifier using a known distribution type. So you're assuming that the distribution is Gaussian. Very, very simple to do. And there are built-in algorithms for this in MATLAB, as well as in Python, as well as in R, depending on what you may be using. And Dr. Rosen is intimately familiar with this algorithm. In fact, she has recently published an article that uses naive Bayes in her work. All right, K-means. K-means is a clustering algorithm, not a classification algorithm, a clustering algorithm, meaning there are no labeled data. The goal of the algorithm is to find clusters of data that includes lookalikes. Okay, so it looks at proximity of the data to each other. It is therefore an unsupervised algorithm, and it is very easy, very, very, very simple. This would be the first clustering algorithm you would try if you were dealing with unsupervised data. And the way it works is as follows. Let me show you a bit cartoon. Imagine that these are the data that you have. Okay, you don't have labels, so you don't know which one is which one. So the first thing you do is you pick a K, just like in KNN. So that is the number of clusters that you would like to create. Let's say you pick 2. All right. You randomly pick 2 points as your cluster centers. Doesn't matter. I picked this one and this one. Heck, it doesn't even have to be one of the data points. I could pick cluster centers, say here and here, for that matter. But generally, you would pick 2 data points. Yeah. Now, you are going to look at its nearest distances. You will see that these 3 are closest to this guy, and this one is kind of far away. Okay. Now you're going to calculate the mean of this data sets, of these clusters. So in this cluster, the one that is centered at blue, there's 1, 2, 3, 4. And in the other cluster, there's just this guy alone. So I'm going to compute the mean of these 4. And that just moves here. This one is just itself, so that doesn't move. Now I'm going to calculate, I'm going to put each instance to its closest center. So in this case, these 3 are closest to this mean. And this one are now closer to each other. Now I repeat, I'm going to recompute the mean. Now I'm going to compute the mean of these guys and compute the mean of these 2. Now the mean of here moved, the red mean moved between the 2, and this one moved here. And you keep doing this over and over and over until the means don't change, don't move anymore. And then that's your clustering. So if at the end, probably these 3 maybe will, or maybe these 2 will be classified here, and these 3 will be here. Who knows? You can try this at home. Does that make sense? That's k-means. And by the way, let me go back here. K-means is also available in just about all platforms. In MATLAB, it's k-means. You can find it in R as well as in Python as well. Okay. Okay. Next up is a decision tree. Now, earlier when I asked which algorithm you would pick, a few of you picked a random forest, right? A random forest is a collection of decision trees. A decision tree, or more formally, a CART, classification and regression tree, is a hierarchical organization of series of if-then rules. With those rules, you create a tree. The tree starts at the root node and represents the most important, most critical question to be answered by the model or by the tree. Okay, and then the root is connected to other internal nodes, and they're connected with these branches or links, each representing a particular attribute. And each branch, each attribute is then split into further branches based on the values of that parent node. So the decision tree progressively evaluates all features, starting with what it believes the most important one, and determines what are the other important ones, and determines a critical value to split that feature. Okay, so here's an example. Let's assume that you're trying to classify fruits based on color, size, and shape and taste. So those are your features. Your algorithm, the decision tree, decides that color is the most important features, and splits into three: green, yellow, or red. If it is green, the next most important feature is size. And based on that, the three values are big, medium, and small. And the algorithm decides that the labels are watermelon, apple, and grape based on that values. So any given fruit would then be going through this classified decision tree as follows. You have an unknown fruit. You look at the color. Is it green, yellow, or red? You look at it and you say, well, it's red. He says, well, is it small or medium? Well, it's small. Then he says, well, is it sweet or sour? Well, if it is sour, it's grape. If it is sweet, it's cherry. So this is a simple example of a decision tree. Now, of course, the question is, the two most important questions are, A, how does the algorithm determine which features are important? And B, how does the algorithm determine what are the splitting values of those? Okay. Now, for that, I have a series of slides here, a starter guide for a self-study on classification and regression trees. And in these, I give you the definitions of the terminology, and then I'll show you how to do that. And I'm not going to go through this in this because I'm going to cover other things. But it will go through step by step how does one do that, and it ends with an example, okay, for the famous Fisher Iris data set. Okay. What I would show you, however, how to use this and a couple other things that we have seen so far, which is the naive Bayes as well as the KNN, using MATLAB without using any coding to develop that. Okay, so if you have MATLAB and you want to follow with me, this would be a good time to start that. So I'm going to stop sharing this. And I'm going to share my screen with you in a moment. once I set myself up. All right. Clear everything. So what you need to do is run MATLAB. So I'll while I'm making these initial remarks about MATLAB, start doing that. And then once you have it, it may start somewhere. And let me do this. And then move this here. I'm going to share my screen with you again. I have to make sure that it is the right one. All right. Actually, I'm gonna share my entire monitor because we're gonna be using multiple screens there. There you go. Let's do this. All right. Can everybody see my MATLAB? When it starts, it will probably start with the editor here. You won't have this. So let me close these so that we'll open these later. Okay. It may start something like this. What I need you to do is go to the directory where you have that folder that I sent. I presume you unzipped this. And in my case, excuse me, it is on my desktop. So I'm going to go to my desktop and I will find machine learning files. I'm going to double click on that. And on the left side, it will show all the files in that directory. Okay. So I'll wait for a few moments for everybody to be able to get there. So hopefully you're looking something that looks like this on your screen. Okay. Let me know if you've been able to unzip that folder, the one that says Machine Learning Workshop Files, and you have it somewhere close to you. Okay. Yeah, just say yes on the chat window, so I know that at least some number of people have done this. And also let me know if you have open MATLAB and you can see at least this much. If you have difficulties starting MATLAB, let me know if you. Okay. All right. So the M files here are scripted files. Those are codes that I have written previously, and I'm sharing them with you so that you can use them, tweak them as well. But we're going to do a couple of things that does not require that as well. Now, in the top here, you can see it says Home, Plots, and Apps. If you click on Apps, you will see a number of icons here. And then there's a pull-down menu here. If you do pull that, and you'll see a whole bunch of other apps in there. These are MATLAB's built-in applications that allow you to do a lot of things without really running, without writing much or maybe any code, or maybe very little bit of code. Okay. So the one that we're going to start with is Classification Learner. So just click on that one. It will take a few moments for it to initialize. And again, when you have this window, let me know. All right. Okay. So now we need data. So there is 4 files there. It says OPT class, OPT test, OPT train, OPT test class. This is a optical character recognition problem. Excuse me. So go to the main command window and simply type load OPT train, and also load OPT class, and also do the other 2 because we'll OPT test and load OPT. What is it? OPT test class. On the workspace, you'll see that on the right, it shows workspace. These 4 matrices have been loaded into the workspace. There are 62 features here. And these are pixels, essentially showing images of 0, 1, 2, 3, 5, 6, 7, 8, and 9. Okay. And you can see that the training data has 3,800 examples. Test data has 1,797 examples. If you're able to load all of these, let me know. And now we can go to the Classification Learner app, click the new session, and choose from workspace. All right. It will want you to specify the data set. Under the says data set variable, if you click on that, you will see those 4 files that we have loaded to the workspace. Choose OPT train. It also tells you it is a 62 by 3800 matrix, because there are 62 features and 3,823 data points. Click that one. And you will see that it says extracting predictors and responses. And at the here it thinks that the data is in the column. It says use columns as variables. And if you look at the predictors here, there is like 3,000 whatever many columns. Our data is in the features, not in the. I'm sorry, our data is in the rows. There are 62 features. So instead of columns as variables, click on the next one. It says use rows as variables. And now you will see that it says it's at 61 predictors, and then there's row 62 is there. That's somewhat grayed out. That's because it thinks that the row 62 is the response variable. In other words, the class variable. But that's not the case. Our labels, we're also going to read this from workspace. So click on from workspace. Oh, forgot to do one thing. So let me type this in your MATLAB command prompt as well. OPT class is equal to vector int OPT class. What this does, it converts a matrix into a vector. OPT class, and I'll show you what it looks like, was a 10 by 3,823 matrix. Now it became 1 by 3,823 matrix. And if you look at this, if you double click on OPT class, you'll see that it's 1, 1, 8, 5, 7. These are the class labels. So the first one is 1, the second one is 1, the third one is the number 8, the fourth one is number 5, and so on and so forth. You can close this by clicking on the X here. Okay. Now, once you do that, I need to refresh. OPT train. Okay. I was asked, can you please repeat from loading? Sure, let me close this. Did you do the loading part? So I presume everybody load the data, right?
Actually, I don't know what's going on, but as soon as I do the first load OPT underscore train, and then I enter for the next line and it says error using load.
What does it say? What's the error?
It says error using load, unable to find the file. So
okay, sure. That's because you are not in the correct folder. Now, do you see this at the top where there is the path? You need
Yes.
to go. You need to go to the directory where you put that ML workshop files. So I presume you downloaded it and unzipped it, and it's somewhere in your
I did
desktop.
that.
Okay.
Yeah.
So let me go back here. So maybe you are
Can I
different.
share my screen if you don't mind?
I'm sorry.
Is there any way I can share my screen to show you what exactly I'm up to?
I don't know whether there's any way to do that. The only way that is you would have to share your screen, but if you do that, then nobody will be able to see my screen.
Oh,
Right.
okay. Okay, no worries. Yeah.
But here's what you can do. At the top, wherever you are,
Mhm.
wherever you are, okay, if you will see the file structure here. Find this folder where that ML workshop files are located. In my case, it is under users or Polycar, desktop, and machine learning files.
Mhm.
So if I double click there on the left, you should see all these files here.
Yeah, I can see that.
All right. Now, if you do load, it should be able to load it.
No, it's okay.
Then I don't know. Then there's because.
Yeah.
All right. So it worked for others. Okay. Well, you'll see. You'll be able to follow. I'm going to put one more command here. So type this one as well. It's the same thing we did the OPT class. We're going to do the OPT test class. Essentially, we're changing it from a matrix to a vector, and we're going to use them in a moment. And this is all the typing you will do for now. Everything else will be just click and choose. That's just to be able to load the data. All right. Now here I'm going to say new session from workspace.
Hi, sorry, excuse me. Yeah, sorry about that. I fell off where you inputted the training data. What was done after that?
Are you able to load the data?
Yeah, I already loaded, opened a new session from my workspace and
Okay. Before you do this, let me close this. Make sure that you have these 6 lines in there. So if you have these, then your data sizes will look like this on the workspaces. On the right side, OPT class is 1 by 3800 vector. OPT test is a 62 by 1797 matrix. OPT train is 62 by 3823. And OPT test class is 1 by 1797. If you are here, if you're able to get this far, then that's all the coding that you will need. From this on, it will be straightforward. Yes?
Okay, thank you. Yeah,
All
I'm
right.
there.
So I'm going to click on the classification learner. I'm going to start a new session. Click on this arrow, click from workspace. It says select input. I'm going to choose OPT train. Right now, it thinks that there is 62 data points, each 3800 features. That's not the case. It's the opposite. I'm going to choose rows as variables. And in the response here, also, I'm going to choose the response, which is the correct labels from workspace. Click on workspace. And you will notice that it automatically picked OPT class as the response variables because it recognized that there are 3,823 data points, and there is a variable there. It's 1 by 3823. It figured all those must be the labels, and that is in fact the labels. Okay. So that's it. So hit start session. Is going to load the data. Now it says here, says 1 tree. It says find tree. You may get a scatter plot. You can ignore that for now. There is another tab here that says summary. If you click on the summary, it shows you the parameters of this tree. Okay. By default, it picked tree is the first classifier. Now we're going to pick others from here as well. Now, over here it says models, and there is a drop-down menu here. And if you click on this, it has all of the models that MATLAB can create for you. Let's pick a few of those that we recognize. It already picked a tree, so let's leave that. Let's pick Gaussian naive Bayes. Just click on it, and it will add it to the list of models here on the left. And then let's pick, we haven't done support vector machines yet, but let's pick medium Gaussian. Sure, why not? Let's pick that. And then that will be added to the models as well. And then let's see, what else do we have here? Nearest neighbor classifiers. There is a find KNN. Let's pick that. And also let's pick a coarse KNN, right? So not as fine. So let's have those. We will later see SVM, so let's pick SVM kernel. And let's pick a medium neural network. I picked 7 different models. You will see that in that models drop-down menu, you could pick all quick to train. So if you pick this, it will just add 7, 8, 9 models that are quick to train. You could pick all models. So that means MATLAB will train every possible machine learning model it has, but that will take a long time, right? But for now, this is a good list. Oh, wait, did we do? Yeah, we did do naive Bayes. We had a decision tree. We have a naive Bayes. We have KNN, and we have a neural network in here. Now, if you click on any one of these, it gives you the parameters that you can adjust. For naive Bayes, there is no parameter to adjust. Naive Bayes is, well, naive Bayes. Okay, there is nothing, there has no parameters. KNN, number of neighbors. So because this is a fine KNN, it picked K is equal to 1. That means it's going to look at its nearest one neighbor. How do you add more than one model? You just go to the question was asked, how do you add more than one model? You simply go to the models tab at the top, look at, click on that arrow, this arrow here, and then choose whichever one you want from here. Okay. Now for the coarse KNN, notice it has number of neighbors, so I can adjust that instead of 100. So this would be a K is 100. I can change that to say K is 15. I'm sorry, it's when I click on one of the previous sections, go. No, wait, it overrides when I click on one, the previous selection goes away. Huh. That is unusual. It should simply add it to the right. So if I were to pick someone here, let's say all naive Bayes, it just adds all naive Bayes. I am not sure why it overrides it. Is that what everybody else observes? So when you are you able to add multiple models to the left side here? Again, if you're able to do that, just say yes. If not, okay. So at least one person can add. I don't know what the override issue is. There must be a setting somewhere that allows you to. All right, it's not that critical. It's not that critical. Just pick one of them because it's the same process, regardless whether you have one or more. And once you're done with that, just simply set. We can train all or train selected. Just hit train all. It will use parallel processing. If you have multiple cores on your machine, it will open the parallel processing and it will use all of those. This may take a few moments. And you can see it in real time. It is training. In my case, now it's the first 4 are being failed. Notice that naive Bayes failed. So it's already trained and it failed. Now here, the first one, the tree is done. It has a validation accuracy of 88%. Notice that the KNN is at 98%, 97.9. Now, by the way, what is this evaluating it? It is using of those 3,800 and whatever data points, 5% of it is set aside for validation. You can change that amount. So it is testing it on that 5% data that it's set aside. We're going to use a separate test data in a moment once the training is done. You'll notice that both types of naive Bayes have failed. It was not able to train a naive Bayes. Using the Gaussian kernel, it uses a different kernel. Let's see if it is going to be able to do it. The difference between these two, Gaussian naive Bayes and kernel naive Bayes, The Gaussian naive Bayes assumes that all of the probability distributions are normal distributions. The kernel naive Bayes is doing what we did, that is creating those histograms using some kernel, some function, and trying to fit a histogram to the data. And that's why it's taking much longer. All right, and the SVM is still training. So, but a few of them are finished. Now, let's pick one of them. Let's look at the tree. This is a fine tree. And what it's showing is that confusion matrix. Remember, we talked about the confusion matrix in the first hour. What we hope to see is large numbers on the diagonal and a small or zero in off diagonal. Everything in the off diagonal, those pink boxes, are the number of instances that are misclassified. So for example, the 6 is the true class. There were 6 data points that were class 5, but were in fact classified as class 2. But there were 318 class 5 instances that were classified as class 5. So this is a pretty good correct classification here. Okay. And about 88.5%. Now, if you look at what's the best one out of here, this KNN, notice that it actually did better than a medium-sized neural network with a 97.9%. If you click on that, you will see the confusion matrix for that one. Okay, so we've just run multiple models, multiple classifiers right there using just a few button clicks. Now, what if you have a separate test data that you want to evaluate on? And we do, in fact. So for that, find this, it says test data button here. Click on the arrow here and say import test data from workspace. You'll get another window and says select input. And here we're going to do OPT test. This is 1797 to be exact. 1800 data points that were not used during training. The classifier never saw that data. Okay. Oh, wait a second. Here it is. Now I need to pick a response, and in fact, it recognized OPT test class as the correct response. So these are the correct values, the correct class labels, 1 through 10. And so we're going to tell this to the algorithm so that it can calculate whether the classifier can correctly classify or not. So what's going to happen is after I say import, it's going to load this data. This is test data the algorithm never saw. It is going to run this test data through these models, and it's going to find the labels that the model predicts. And then it's going to compare that label that's predicted to the correct labels that I am also providing. And that way it's going to be able to compute a percentage of correct classification. So I'm going to hit import. It will take a little while. And now I'm going to say here, test all. By the way, the training is done. For those, notice that naive Bayes classifier, the kernel based naive classifier did train, but did not perform on the validation data as well as some of the others. Okay, now it's doing the evaluation of the test data. It's still running it. because there are 7, 8 different classifiers, it's going to take a little while. It's not done yet. Wait, why is it not doing? I think it is still. Okay, I'm going to delete these failed ones. And the way I do this is I click on it, right click, and just say delete. Okay, and let me do this again. Did I not? Important. Let's say okay. Let me make sure that I do this correctly. OPT test is the test data. OPT class, OPT test class. Yep, that is import. Okay, that's done. And now test all train models. Now for each of these classifiers, okay, yeah, it is working on it because I can see that it's not responding to my clicks, so that means it is working. Or at least I hope it is. Something is happening. Okay, it did finish. You will notice that if you're able to get all the way to this point, now it shows accuracy test. Now, this is the performance of the classifier of each of these classes on the test data, not the training data, on the test data. Remember, the algorithm never saw any of the test data during training. It is able to compute these test performances because I provided the test data and the correct labels for the test data. Now here you can see that, let's see, the SVM, the support vector machine, performed the highest here. And this is the confusion matrix. Now if you click on summary here on the top here, it gives the training results and some statistics. Like how long it took to train. So it took 240 seconds to train, as well as test results. 96.8% out of the 1,857 of them were misclassified because that's the total cost. And you can change your cost metric through this cost here. Right. And here you get a matrix. I can make this larger. Because there are 10 classes here, it's the 10 by 10 matrix. And currently the cost is every misclassification is a cost of 1. Every correct classification is a cost of 0. Right? So if class 6 is classified as class 6, the cost of that is 0. But any misclassification, class 6 classified as class 1, that's a cost of 1, cost of 1. You can change it. So if you really don't want to misclassify class 4 as class 8, you can change the cost of this to a much larger number, say 10, and then it will try to minimize that particular error. So this is particularly important if you have costs that's not equal, errors that are not equally bad, right? And now you can look at all of the others. So naive Bayes actually did not as good, right? The total cost was 545 misclassifications. The KNN did remarkably well. Right. Okay. And if you look at its summary, its total cost was only 66. So out of 1,800 instances, only 66 of them were misclassified. Okay. So does that, hopefully it gives a bit of an overview of how this work. Now, in the remaining hour or so, I'm going to talk a little bit about neural networks, and we'll come back to this, and we'll do some analysis with this as well. But let me go back. I'm going to minimize these, and I am going to all right. I hope you can all see the multilayer perceptron slide here. So let's talk a little bit about this. So this is our introduction to neural networks. Excuse me. When people say neural networks, typically they're talking about, or at least in our field, they're talking about artificial neural networks. An artificial neural network mimics the structure of a physiological neural network, which is, of course, a massively interconnected web of neurons where each neuron performs a very simple function. And that function is take all the inputs that it receives, add them up, and pass it through some nonlinear function. If the output of that is greater than a threshold, that neuron fires, meaning it transmits that information to the next neuron. Or if that output is less than the threshold, the neuron does not fire, and that information no longer proceeds. So a typical artificial neural network is a model that mimics that structure. Each neuron is modeled with a node, as you can see here. This is a two-layer neural network. You see input nodes in yellow. That's where the data comes in. A red hidden layer nodes. And in this case, 3 blue output nodes. The output nodes provide the classification of the network. So for example, if you have a 3-class problem, there will be 3 outputs. And each of these would have a number between 0 and 1. The highest would be the class that is predicted. So for example, if the output is here 0.8, 0.1, 0.03, the first output is the highest. So that means the network picks class 1. If the output was 0.2, 0.8, 0.1, then this one is the highest. So that means the network predicts class 2. The number of input nodes is the number of features that you have. Previously, we had 62 in that data. So that would be 62 input nodes here. The number of hidden layer nodes is a user-defined parameter. You pick. The larger the number of nodes, hidden layer nodes, the larger the network, the more complex problem it can solve, but the more likely it will overfit. Okay? Each of these nodes are connected to each other using these connections. In an artificial neural network, these connections carry weights. And that's weights, and those weights are where the information resides. Okay. A neural network is trained using what's known as a gradient descent algorithm. And we'll explain what that means in a moment. And that is how these weights are determined. Okay. So let me give you a very brief overview of neural networks. You can look at the formal definition of neural networks in Wikipedia, and essentially it says it's a model that mimics the biological brain. Okay, so what does each of the neurons or each of the nodes do? So this is my artistic rendering of a neuron. There's a cell body, there's a long axon, and there are these little terminals. The information to a neuron comes from dendrites. The information is processed in the cell body. It is sent down this axon to the synaptic terminals. If the neuron is going to fire, that information is sent down to the axon to the next neuron here. So we make a model of this, and that model is here. I have D inputs, as if like D neuronal inputs coming to this neuron. And all that this node does is as follows. It simply multiplies each of these inputs with this weight. X0 times W0, X1 times W1, Xi times Wi, Xd times Wd. Okay, it adds them up. And then it passes it through some nonlinear function that we call activation function. I'm going to show you what those are in a moment as well. And that's it. That's all there is. Each node does. So if this is a biological neural network, you have these neurons coming in and giving, sending their inputs to the next layer of nodes, and those are sending their inputs to the next layer of nodes, neurons. Well, that's a mathematical model of the same thing. Okay, so that's the physiological origin. But the connection ends there. Now, the way that the ANN is used is, again, you have a training data. You present the examples and the desired outputs, the known labels. And using that, the neural network during the training determines what these weights are, these connections are. And once those connection weights are determined, you provide new data, and the neural network provides its predicted outputs. Okay. Formally, this is what happens at each layer. Let's call this as net J. Net J is nothing but the weighted sum of its inputs. That is X1 times W11, X2 times W12, Xd times W, so on and so forth. And then that passes through a function f. And that function is simply one of these. We believe that the biological neurons use a threshold function. That is, there is a threshold. Here, that threshold is 0. If it is greater than the computed value of the node is greater than threshold, it fires. Otherwise, it doesn't. There are different versions of activation functions that we can use. Some of them are shown here. And that's really all it does. A neural network, for each node, it computes. I'll go one more back. It computes its weighted sum of its inputs. These are the weights. These are the inputs. Multiply each input with its weight, add them up, pass it through this one of these functions, which is one of these. Oh, went too far. Sorry. One of these functions. That's it. That's what a neural network does. And all of the complex machine learning algorithms that you see, that you hear, that are based on neural networks, whether it's deep learning algorithms, convolutional neural networks, they're all based on this simple idea. There are these massive number of nodes, but all that each node does is compute its weighted input, pass it through one of these functions, and send it to the output. That's it. Okay, now the secret sauce here, of course, in the weights. So how do we find the weights? In order to find the weights, we define a criterion function or an error function or a cost function that you want to minimize. That cost function could be something that relates to the number of misclassifications that you want to minimize. And then the whole algorithm, the whole process is reduced to a search of minimizing or finding the minimum of that cost function. How does this work, you ask? Well, here's how it's done. Imagine that this is the unknown error function that you find, that you want to find the minimum. Here is the W. There is a W that you don't know, a weight, for which the error of your classifier is minimum. Now, you don't know what that is. Looking at this figure, you can see that it is here. It is right here. This would be, the weight here is the weight that minimizes this error. But here's the problem. You don't know what this green error function is. That is unknown to you. You can calculate the error for any given W. For any given weight, you can provide an input to your network, see what the output is, and can compare the output to a known correct label. And if it is correct or incorrect, you can compute its error. And that's this value here. But the function itself is not available to you. So the way gradient descent works is you first make a guess. Say I picked W1. Now, I don't know if W1 is correct. I just picked it. I calculate the error associated with W1. And I calculate the negative derivative or the gradient of that with respect to weight. And that's what's represented here. And I move from this point towards the negative direction by an amount called eta. Eta is step size. Okay. And then I repeat the exact same thing. Now I reach W. I calculate the error for W. I find this. I calculate the derivative of this with respect to W. And that gives me this. I move in that direction. And this iterative approach will eventually get you to the bottom of this error surface. And you will stop when your next W is no longer different than your previous W. That means you've converged. Okay, so that's gradient descent in a nutshell. Now, you don't need to know the details of this. What you do need to know is there are some issues to consider. We mentioned a learning rate. That's how big of a step that you're taking. That is how big of a step you're taking from here to reach your next one. Okay, to reach next one. If you pick your learning rate too large, you can jump from here to here. You missed the minimum. If you pick too small, it will take you many steps to get there. It will take the training table long. Right? So there are, how do we terminate to avoid overfitting? There are lots of parameters to choose. We're not going to talk too much about that. But what I'd like to do is give you another demo that makes this, that kind of visualizes this a little bit easier. Okay, so what we're going to do now, let me close this. We're going to go back to MATLAB. Okay, if you have these data that are already here, leave them as they are. But this time, type and start. And start, if you type that, you will get this window. It is asking whether you want to do curve fitting, classification, clustering, or time series analysis. In this case, we want to do classification or pattern recognition. So click on that one. After a little bit, you will get this. I don't need this. Okay. Now, what this is showing you is a generic neural network. Okay. This particular neural network, by default, has 10 hidden layer nodes, and I know that because it says 10 here. Here is the input. Here is the hidden layer. Here is the output layer. Now we haven't set this network yet. Okay, so we're going to do that by importing data. So we'll do the same thing. We're going to import data from the workspace, the first one. By the way, this NN train does more or less what we did previously. It's just a different user interface. Oh, all right. So I get this. It sees that I'm going to pick OPT train again. That's the training data. Responses. Okay, so the data is in the columns, 3,823 observations with 62 features. But why does it not see? There it goes. Ah, hold on a second. Let me cancel that. I'm going to clear this and I'm going to reload those things. Load OPT. Train, load OPT test, load OPT class, load OPT test class. All right. So hopefully that should work now. Let's do this again. Import data. All right, now predictors. That's my data. That's OPT train. And responses, the correct label is OPT class. And here it says that observations in the columns. The training data is 33,800 observations with 62 features. The OPT class is, those are the labels. This is a 10 class problem. Again, 3,823 observations with 10 classes. I say, okay. All right. Now I have 62 inputs, 10 hidden layer nodes, and 10 classes because it has 10 outputs. I can split the data, 70% for training, 15% for validation, 15% for test. And here I can choose the number of hidden layer nodes. Let me pick 5. Well, let me pick 3. And just hit train. So this will be a very, very small network. So it's training. It finished. It stopped because it reached maximum number of validation checks. I'm going to show you how to change this in a moment. And then it shows the errors here. Not too bad, not too bad, not too bad. Okay. So now I want to test the train network on an additional test. But before that, let's look at the confusion matrix. This is on the validation data. Let's see how well it did. Make my screen larger so that you can hopefully see these a little bit better. So, oh, there we go. There we go. All right. So here's the confusion matrix on the training data, validation data, test data, all of the data. So if you look at this bottom right corner here, so it did about 80%. 80% correct, 20% incorrect. So let me change this to a slightly larger network. Let me make this 10 hidden layer nodes and retrain. It says it's going to clear the existing model. I say yes, okay, go ahead and do that. It is training. It is done with the training. Let's look at the confusion matrix again. Remember, with 3 hidden layer nodes, we did only 10. We did 80%. So with 10 hidden layer nodes, let's see if we do better. takes a little bit. All right. And now you can see it's 98%. So clearly the performance went up significantly, and I mean significantly, from 80% to 98% when I increased the number of hidden layer nodes. If you keep increasing this, there will come a time when it's going to start overfitting. So you have to be careful of that. Okay. Now I'm going to do a couple other demos here. Let me close this. Hold on. All right. With some sample data, and I actually, you have the code to do these. What I'm showing here is, and we're going to run these in a moment, and you'll see them. I have 3 different data sets here. There's a spiral data, some randomly generated Gaussian data in 3 classes, red, blue, and green, and what I call checkerboard data. Notice that the checkerboard data looks like a rotated checkerboard. I'm going to train a classifier on this data, and then I'm going to ask the model to classify the entire grid of data here and then paint it. And if you do this correctly, this is what's going to come out. And it'll show you how well the neural network generalizes. Okay. So for example, here should be green because that's closest to the green. Over here, it should be red, even though there is no training data from here. We want the neural network to extrapolate. It should be red when it's painted here, and so on and so forth. So the way to do this is we're going to run this code called train MLP menu based. Now, I hope you still have this on the left side. If you do, click on train menu based, I'm sorry, train MLP menu based. And here you're going to see the code for doing this, that generate the data. Okay, you don't need to worry about it. We'll just run it. And all I need you to do is just click run. If everything is set up correctly, you will get, 1 second. You will get a pop-up window that is, hold on a second. That has choose data set on it. Can everybody see that? Choose data sets. Yeah, okay, so at least one of you can see it. I'm trying to move that window to the other monitor so that you can see it, but you can see the code window. So did you click run? Mike, you said you can only see the code window. If you click run, you should get another window. It says choose data set on it. Yes. Okay. All right. All right. So if you all have that, just click on, say, Gaussian, and then that will, you will get a verified data size. Say yes, and then you will see a partitioning data. It will allow you to choose error goal and so on and so forth. Just leave those numbers as is, as hit OK. You'll get another data partitioning window, hit OK. And then it will start training. And you will get this window. And hopefully this window. All right, so it is training. And you can see that I set the maximum number of iterations to 5,000. So it will go up to 5,000 iterations. You see where it is right now. You see its performance. I set an error goal of 0.01. I want the error to be less than 0.01. And the validation check is, and it is going to hit that. And it is done with training, and it will give you this. And as you can see, it classified all of these regions into blue, red, and green. Let's close these. Hit run again. This time, pick checkerboard as your data. You will get a, you'll ask if the data is correct, just say yes. And then you'll get another, says data partitioning, error goal 0.01, number of maximum iterations 5,000, clicks yes. Now you get another data partitioning to just say okay. And then it will start training. And here's your data. This is your training data. In the training data, the algorithm is provided with these data points and whether it's a red or a blue dot. But then we're going to test it on a whole bunch of other points that are white here that are not specified. And we'll see how well it can do in that case. At any point, you can stop the training. So if you feel, I've done enough training, you can press this button here. It says stop training. If I do that, it will stop the training there. It would use the current values of the classifier, and look what happened. So it didn't do very well, right? Because it wasn't properly trained. Okay. So in order to do that, let me close this again, and I'm going to rerun it. But this time, I'm going to choose checkerboard again. Right. I'm going to leave the error goal there, everything, leave them there. I'm going to leave the others there as well. But I think we're going to wait this time for it to finish. You can look at the network diagram here. If you click on this network diagram, you will see the network architecture. And right now it has 2 inputs because it's 2-dimensional, 20 hidden layer nodes, 2 output nodes because it's 2 classes. So it gives you a visual confirmation that it is set up correctly. Now, there's a couple other buttons here. If you click on performance, it is going to show you how well it is doing on the training and validation tests. Notice that it is currently at roughly 0.175. The goal is 0.01. So it's going to try to reach 0.01 during its training. I recommend that you don't keep this window open because it's going to make it run slower. So look at the number of epochs changing, 481, 85, 86, 87, and that after I close that, you will notice that it sped up dramatically. It's chugging along. let's wait until it gets down to 0.12, and then let's stop it. Or maybe let's stop it at 1,000 iterations. And see if it helped at all. Mind you, there are 20 hidden layer nodes now for this. All right, let me stop it right there and see how well it did. All right, you'll notice that, it's a little bit better compared to previous one, but still not quite there. So this is what you will do. And this is the reason I'm going through this is because this is very typical. So you're going to go back and forward trying to find the right parameters for this. So that means I'm going to run this again. And let's do checkerboard again. And this time I'm going to change, let's change it from 20 hidden layer nodes to 30 hidden layer nodes. All right, and let's see what happens then. So I increased the number of hidden layer nodes. And we'll see whether that makes any difference. All right. While it's doing that, let's leave it to its own devices. And we'll I'll talk a little bit about, let's see, okay, we have about 20 minutes left. I want to talk to you a little bit about perhaps one more algorithm. We're not going to go into the mathematical details of that, but it is commonly used, particularly in biological data sciences, and that is support vector machines. In the background, that MATLAB is running its training. By the way, if you think this is taking long to train, in real-world applications, it is not unusual for classifiers to take hours, days, weeks, or months to train if these are really, really large problems, large data sets. Okay? All right. So support vector machine. So support vector machine is a very different animal. It is not a neural network. It is a statistical classifier. It's based on optimization. But the fundamental premise of support vector machines is very, very clever. The thinking is as follows. If I have data, well, let me actually go to here. Imagine that this is my data here. Two class problem in 2 dimensions. Some red data, some blue data. And because this is such a simple problem, I can draw a linear line between the two as the decision boundary. But I can draw many such lines. There's not one solution here. There's many, many solutions here. So the question is, which one is the best one? Now, you can have an intuitive answer to this, and you may think that the one that's kind of in the middle is probably the best one. And if that's your intuition is correct. So support vector machine finds the decision boundary that goes smack through the middle of the 2 classes. And how do you define the middle? It finds those instances that are at the boundary of one class, and those are indicated these 3 triangles on this side and these 2 blue circles on this side. And those are what the algorithm called support vectors. And then it tries to find the classifier that maximizes the margin between those 2 support vectors. right? Now, if you look at this example here, I have data circles here, pluses here. I can have two separate classifiers. I mean, there's infinite number of classifiers that separates these, but this diagram shows two of them, direction 1, direction 2. If you do direction 1, the margin between the support vectors is this much. But if you choose direction 2, the margin between its support vectors is that much larger. So direction 2 is a better model. And support vector machine simply finds that model. Okay. Now, there's a bit of math involved in this that you don't need to worry about. And the slides that I will share with you has all of those introductory math, and I'm not going to get into those. But there is one important thing that you need to know about support vector machines, and that is by their design, it is only good for two-class problems, like the ones that I showed there. But most real-world problems are not two classes, nor are they linearly separable like this. And support vector machines are known as kernel approaches or kernel-based approaches. And there is a kernel trick to the support vector machine, and that's what makes this so ingenious. Support vector machines create a transformation that converts a non-linearly separable class into a linearly separable class. So here's an example of this. You see the X's and the circles that are not linearly separable. The kernel trick of support vector machines converts this problem into this. And now they are linearly separable. And that's why support vector machines are so so powerful. Before deep neural networks, support vector machines were, and in some cases still are, the most popular classification algorithms for biological, specifically genomic data. But now support vector machines, or SVMs, as well as deep neural networks, are both commonly used. All right, I'm going to check back with my MLP here. Its error is down to 0.05. Let's give it a try. I'm going to stop it there and see how well it did. And voila, you can see that this network is far better trained. And you can see the decision boundaries. Had I left it continue all the way to 5,000, these boundaries would have been even much sharper. Okay. So if you want to try these different things, you can. Let's see what else do I have here. Let me stop here and open the floor for any questions, and or any other demos that you may want to see. We can do a lot of different demos here, but I want to pause for a few moments and see if we lost anyone, and then kind of put things back together, right? So if there's a question, feel free to unmute yourself, or just ask the question on the chat window. I'm monitoring that as well. Okay. Would the recordings be made available after the workshop? I believe that is the case. Dr. Rosen will be planning to put these on YouTube.
It may take up to 2 weeks.
Okay, so it may take a couple of weeks, but for these, because there's going to be large video files to process and put them on there. But yes, so they'll be there. By the way, I have a train SVM function in there as well. So if you double click on that one, train SVM menu base, and if you run that, we can do the same thing. Now, one of the advantages of the SVM is actually it will run in most cases faster than an MLP. So let's do the same checkerboard example there. And of course, SVM has different parameters. So again, you're going to have to play with these. So here's the training data. And it's done. We'll see how quickly it is done, except it is not a very good one. So you can see that it didn't create my checkerboard very well. So that means my parameters were not set correctly. So I'm going to try it again. Now I'm going to run checkerboard again. And this time, I'm going to pick different parameters. Let's the big parameter here will be the kernel parameter. Let me change that kernel parameter to 0.1 instead of 1. And if I do that, and look how quickly it trained. Remember previously with the neural network, we waited for like 5, 6, 10 minutes and it wasn't done. Whereas with the SVM, it was just like that. So that is the advantage of the support vector machines. It will run very, very quickly. And if you pick the parameters correctly, look how sharp those edges are, how well it did on that data set. You want to try it with other, let's see, a spiral data set. I'm going to show you the data set. So these are the default parameters. I'm just leave them as it is. And here is the training data and the test data. The training data is only these that you see. The test data is everything that you see in this entire grid. And you can see that it extrapolated these areas as well. I have another one. There's called banana data here. Here is the banana data itself, and here is the SVM-based classification of the data. And you can see the misclassified ones are right here. There are a couple misclassified here. And it also generated a confusion matrix, 96%. But if I pick wrong parameters, folks, same data set. Let's say I didn't put 1 in there and I put say 0.01, which is the value that I use for the checkerboard data set. Now look what happened. All right, here is the training data. Here is the classification data. You'll notice that SVM classified everything into red class. So the correct, the performance is only 50%. Half of them is only correct, the other half is incorrect. So the point here is the fact that every algorithm except Bayes have parameters that you need to select. And one of the experience that you get with machine learning algorithms is to figuring out what the correct parameters to use with any given algorithm. And that is something that you learn over time by trial and error. And you'll get an understanding, you'll get an appreciation, you'll get a gut feeling of which parameters will work, which parameters will not work for various different classification algorithms as well as the data. Okay, all right. So you have all these, you have these data sets in there these are synthetic data sets. This code generates the train MLP and train SVM. You also have an optical character recognition data set. That's essentially images 0 through 9, handwritten. It's just trying to recognize this. That's a 10 class problem. Now, if you want more data, there are a lot of data sets available to you. And let me share this. And again, I'll share this So these are a lot of data sets that are built into MATLAB. So if you want to play around with different data sets, you can see all of these data sets. And many of these data sets actually come from what's known as the UCI repository. UCI is the University of California, Irvine. Many years ago, they started a repository. The last time I looked at this was in 2015. There were 332 data sets there. So let me actually, just out of curiosity, let's see if it's still there. And then how many data sets there are there today. All right, today they have, hold on a second, let me show you this. Today, they have 622 data sets. Okay, and then you can, and these are labeled data sets, by the way. These are data sets with correct labels provided for you. And in there, you may be able to find some biological data sets as well. Are those 600 plus data sets. So feel free to explore, try, play around, what have you. Okay. There are a lot more in the slides that we didn't go there. There's more details about individual algorithms. There's more about boosting algorithms. There's more about a little bit of the math for the neural networks, this SVM, the decision trees as well. I will share those with everyone. But for now, if you have any last minute questions, I'm happy to answer. Tomorrow, Emre will, I believe he's going to do a Python Google Colabs based practical applications for deep neural networks. Any questions, any suggestions, any concerns before we adjourn for the evening? Okay, hearing none, sensing none. Dr. Rosen, back to you.
Thank you so much, Ruby. Yes, I hope to get the slides for, huh?
Yeah, there's one question. How would you apply these algorithms to nucleotide sequences? Excellent question. So the with any data, you have to extract your features first. Okay. Now, the features themselves could be whatever that you feel is appropriate for your classification algorithm. So you mentioned nucleotide sequences. So what do you want to do with nucleotide sequences, for example? Do you want to do taxonomical classification, or do you want to do functional identification, or do you want to find the folding structure of a protein? What is it that you want to do? Depending on that, okay, taxonomy, excellent. So then you would have to extract features from that data set. What could those features be? Well, one feature that I mentioned is histogram of certain k-mers. So you may want to look at, which k-mers occur most often in your sequences, and the number of times that those k-mers occur could be your features, right? So you create your data set from that, and for each organism, you have a data set of different k-mers occurring certain number of times in their sequences. And then you feed that data into a neural network or an SVM or a KNN or whatever it is that you're doing, exactly like the way that we've done. So your training data essentially is a matrix. Each row of that matrix is a different observation, a different sequence that you obtain. Each column is a feature that you've extracted from that data. right? So rows and columns. And in the example that I showed here, where it says, what's the input data, you will provide that matrix as your input data. What's the response matrix or the response vector? That will be the correct labels. That vector will have the same number of rows as the number of instances in your training data, because you have one label per data point. And then you will provide that to the neural network. And then if you're doing it the way that I've done it, you're just going to hit play, or not play, rather run or train or whatever that is. Okay. And as Dr. Rosen said, on Thursday, we have another colleague who's going to be doing demos on logical sequences.
Yeah, so Dr. Sakansanj is going to be showing us how to use neural networks to examine both amino acid sequences, as well as perhaps, I forget what the demo is this year, but if it's the same, it'll be looking at how to classify antibiotic resistance on AMR genes versus non-AMR genes. So anyway, yeah, so he's going to be teaching the workshop on Thursday about that. Thank you. And Roby, you'll send me the slides today?
Yes, I'll send you the slides.
Yes, so you'll
As I
learn
said,
ground up.
there are